Hello, welcome in the 11th lecture of two-phase flow and heat transfer. Today we will be discussing the second part of measurement of two-phase flow and signal analysis. In the previous part we have discussed about conductivity probe, electrical conductivity probe and optical probe. Here we will be continuing from there. Majority of the portion of this lecture I will be covering for multi sensors or multi probe and the signal analysis of multiple probes. Okay. So, as the outline of this lecture, I will be speaking that in this lecture we will be highlighting the essence of signal analysis first. In the previous lecture we have shown you signal analysis, but today in this lecture I will be first giving you what is the essence of that one and how features can be obtained from the signals. So, the essence of signal analysis for evaluation of quantitative data will be explained. Next we will be showing you using multiple signals from the sensors how data fusion can be done and quantitative informations can be obtained. Okay. For that I will be showing you information from some statistical features and some neural network. Also I will be discussing about some modern techniques for signal analysis like scatter plot, attractor, okay, time delay plot and so on. Okay. I will be also showing you that how using multiple sensor data in one array I can reconstruct the interface. This is for highly well defined interface. So, I will be showing you that technique also. Okay. Now, to begin with, first I will be showing you what is the essence of all this signal analysis, or you can say the transforms from the signals. So, I will be showing you what is signal transform. Okay. Now, signal transform for signals we will be considering the signal as some sort of output of a probe which is changing with respect to time. So, we are having variation in time domain. Okay. So, let us say the time is progressing in one dimension and there will be variation in the signal in the other direction. Okay. So, it can be voltage, it can be current, it can be flow rate or any other data which is varying with time. Okay. Now, using transform, what we can do using transform, we find out what is the typical feature of that time domain variations and what are the dominant frequencies and what are the dominant modes of that signal whatever we have obtained from the probes. Okay. So, typical signal transformations are Fourier transform, which I have shown you in the previous lecture also, first Fourier transform, and here also we will be showing you some new signal analysis techniques. So, essentially signal transformation is required from a time dependent data and obtain the important features from there. Okay. Next I will be showing you over here one signal. You see basically here in this plot you can find out this is time, okay, and here we are having some data. This may be some probe signal, optical or conductivity probe or some other type of probe signal. So, here let us consider that we are getting this signal. What I have shown you over here, this is actually a sine wave. So, you can see it is showing a sinuous nature, okay, moving up and down. So, sine wave passing through the same point, okay, 50 times in 1 second. So, here you will be finding out that this is having frequency of something around 50. Okay. So, this I have shown, and once you do the first Fourier transform for this signal, you will be finding out this is the first Fourier data of this signal. Okay. I will not be going into mathematical detail of first Fourier transform because that is a part of mathematics, but I believe that all of you know that how to do first Fourier transform of a time dependent data, and if you do that one you will be finding out that this is the FFT of this signal and you can find out a peak, sharp peak just at 50 hertz. Okay. So, whatever signal we have given over here 50 times in a second, so that came out over here as the peak in the fast Fourier transform. So, once we have some time dependent data and we find out its fast Fourier transform, it will be giving us the dominant peak, okay, where its characteristic lies in. Okay. Next, to elaborate this further, what I have done, I have added few more sinusoidal curves over here, rather cosine curves over here. So, first one you see what we have done, cos of 2 pi 10 t. So, the frequency is 10 in a similar fashion, then plus cos of 25 t, cos of 50 t and something cos of 100 t. So, that means this x t which is varying with time, this can be voltage also, is having actually summation of 4 cosine curves. Okay. So, if I see the raw signal, so this is the time axis and here we are having the x, okay, which is varying with time, you can find out this erratic nature. But if you see minutely, there is some sort of periodicity in this signal, and you can find out these are constructed by actually 4 amplitudes. Okay. So, this 10, 25, 50 and 100 will be coming into picture. Now, to though this is you can observe this one minutely once you see in a close look, but what we can do quickly, we can go for first Fourier transform of this signal and find out what are the dominant frequencies. So, over here you can see I have shown the first Fourier transform of this signal, and interestingly you can note that we have got a peak at 10, we have got another peak at 25, we have got the third peak at 50 and finally the fourth peak as 100. So, you see whatever we have given 10, 25, 50 and 100, that has actually obtained back. So, that means if you are having some unknown signal like this, and if you go for first Fourier transform, immediately you can find out where you are having the frequency peaking. Okay. Now, one interesting thing about these two plots, okay, time domain plot, this one as well as this one, is that here in these two time domain plots, we have taken data at same interval. That means T2 minus T1 is equals to T3 minus T2 and so on. So, that means the probe or sensor is giving you signal at same frequency, that means sampling rate is same. Okay. So, always it is giving at the same rate. But some point or in some measurement device you can find out that this rate is changing. Okay. So, you are having variable time, the sensor is taking variable time to acquire the signal and send it to the computer. So, let us see another signal like this. So, here you can see that signal, raw signal with different frequencies. So, you see over here this is a time domain and here this is some signal, let us say voltage. So, here you can find out these are very closely spaced. So, that means these are very fast signal we have obtained, and here the sensor maybe is not functioning properly or taking some time due to the phenomenon, and you will be finding out that it is taking more time to give you one signal. So, if you see this type of situations in your raw signal, then also we can find out the characteristic features of this type of signal using FFT. So, you see what we have done, we have transformed that signal into a FFT curve. You can find out some peaks also are coming like this. So, from by comparing this one and your previous signal, you see here we have got a sharp peak at 50, but here what we have got a peak at 50, but subsidiary peaks are also obtained at 100, and here we are seeing something around 25, 20, something like that. So, this gives you some sort of idea that at which rate the signals are actually taking time to give the readings to the output. Okay. So, these are the ways how we can find out some sort of quantitative data from the signals. Okay, next I will be quickly moving to different techniques. So, first I will be showing you data fusion, okay, how using multiple sensor and using data fusion you can find out quantitative signals. So, here I will be using a typical flow called core annular flow. So, this is actually liquid core annular flow. A figure I have shown you over here, this is a kerosene figure, okay, kerosene and water figure. So, this core is made of kerosene, okay, and in the annular domain you see here we are having white portions, these are actually water. So, this is liquid core annular flow, and the liquid pair is kerosene and water. So, let us try to see that whether we can capture this core annular flow using multiple sensors, okay, and if we compare the signals between the sensors. Okay. So, what we have done to find out this one, we have taken the help of conductivity probe, but we have taken the help of multiple probes over here. So, let me first explain that what type of probes one can consider. So, first one is that these are called wall mounted probes. So, this is the cross section of the pipeline. So, you see what one can do, they can make through hole in the pipeline, and they can flush this wear. This is all these numbered straight lines are actually wears. Those wears are actually your electrodes, okay, active electrodes, and those are entered in the whole circumference at some particular angular sectors. Okay. So, you see here we have given 8, 1, 2, 3, 4, 5, 6, 7, 8 sectors, and those are entered. Now, all these are wall flushed. Wall flushed means nothing will be extended inside the wall to restrict the flow. So, those are actually just ending at the wall inside boundary. Okay. So, all these are once again connected to the circuitry. The circuitry already I have shown you in the previous lecture. If you remember those wind bridge oscillators, and then we are having Wheatstone bridge, finally rectifier, and then filters, so many things were there. So, all these probes will be going to the signal conditioning units. Apart from this wall mounted probe, we have also given a central probe. So, this is the frontal view of the pipe, let us say. So, wall mounted probes you can see over here. So, this view we have taken along this axis. So, this is actually 7 3 axis. Okay. So, you can see the 7 and 3. Okay. And there will be one central probe, okay, which is actually penetrating the tube and coming in the flow and restricting the flow path also to some extent. So, that we have called as central probe, and we have given that name 0. Now, let us see the signals. So, what we have done, as we are having provision for taking all those 8 plus 0 9 signals. So, we can use actually lots of combinations and parameters permutations. So, what we have done over here, we have found out the probe signals here in this fashion. So, first is 1 and 2, between 1 and 2 already I have shown you where is 1 and 2. So, the signal between 1 and 2. So, what is the signal difference between 1 and 2, that we have shown over here. So, you can find out that we have shown here 3 different conditions: water, kerosene, and water kerosene. So, water kerosene will be giving you corannular situation. Okay. The flow rates are taken in such a fashion that it will be giving you corannular situations. Okay. By the way, these flow rates are once again selected from the flow regime map, whatever I have shown you in the second lecture. Now, if we are having full water inside the pipeline, so you can find out all these combinations are giving you something around 6.5. Okay. All the voltages are in the range of 6.5. Okay. And if you see, if you are having kerosene, okay, then you can find out it is something in the range of 4.56, something in that range. Now, interestingly, what we have found out, whenever we are having both in the form of a corannular pattern, so you see it is coming something around in between these two. Okay. Though you see in the wall, all these are wall mounted probes, you see 1, 2, nowhere we have featured 0. So, all these are wall mounted probes. So, though all the probes are actually connected with the wall interface, because we know in the case of corannular flow, obviously we will be having the water adhered with the wall, but still we see the signal whatever we have obtained, that is not equivalent to the water signal. This is lying somewhere in between. So, what we can do essentially using this type of signals, we can predict back that whether we are having corannular flow or not inside the pipeline. Let us go further and see the data fusion technique. So, here you see I have shown you some signals of the wall mounted probe and the center line probe also. Okay. So, you see all these are with 0. So, 0 1, 0 2 to 0 8. So, you see here the voltage will be coming in between 4.7, which is more near to the signals whatever we have obtained with the kerosene, because the central probe and the wall mounted probe, they are having contact between the kerosene and water also. Okay, because at the core we can have the kerosene. Now, let us see, depending on all these signals, how I can identify the flow regime. So, what we have shown over here, for data fusion we have shown few more probes, as I have mentioned in this previous slides. So, apart from these probes, wall mounted probe and central probe, we have also given two diametrical probe which I have shown you in the previous lecture, and some ring kind of wall probe like this. So, ring kind of wall probe is nothing but a circular ring attached with the inner wall of the tube. Okay. So, two rings we have given like that, and from there we have obtained the signal, and here these are actually diametrical wires. So, these actually these two wires are actually intrusive type. So, actually restricting the flow path, but these are actually wall attached, okay, wall attached ring kind of probe. So, these are not restricting the flow path. So, what we will be doing we will be calling this one as ring probe, and we will be calling these two as parallel wire probe. Okay. So, what we will be finding out using both the pairs of the probe, we will be finding out the statistical features. Okay. And then using these statistical features, we will be going for some fusion. Now, what will be the fusion technique, that is a matter of research, and depending on the flow regime, what flow regime you are studying, the technique of fusion will be varying. Okay. And sometime it will be varying on the flow rates also. So, here I am not going into detail of the fusion technique. So, what best technique is that you can go for some neural network fitting, okay, train the data using some of the signals, okay, and predict the flow regime, and then later on what you can do for some unknown features, and same fusion technique you can find out the flow regime happening inside the pipeline. So, here what we are doing essentially, both the features we are actually fusing over here. So, this is called fusion, and then we go for some clustering. So, what is clustering? So, after fusion you will be finding out the fused data, they are of a wide range. So, then what we need to do? We need to clusterize similar type of signals, okay, and then plot them. So, this is something called algorithm for clustering. So, and finding out the similar type of fused data, and then finally different clusters will be plotting in different places. So, what we do here, we have shown you example of multiple probes and multiple features also over here. So, this is a statistical feature from the ring probe, this is statistical feature from the parallel wire probe. Okay. Let us see that how using this different clusters and algorithms we can find out different flow regimes or identify different flow regimes. So, here I have shown you a flow regime map constructed based on the superficial velocities of air and water, and we have only focused on three patterns: slug, churn and annular. Now, here all these points are identified based on the clusters, as we have mentioned in the previous slide. You see different clusters. So, we have actually fused the signals obtained from this ring probe and parallel wire probe, and finally we have found out three clusters: clusters for slug flow, clusters for churn flow, and then clusters for annular flow. So, you can find out over here we are having a very good cluster over here for the slug flow, here we are having cluster for the annular flow, and finally we are having cluster for churn flow. But there are some limitations of this type of techniques also. Some points at higher velocities you will find out will not be coming in this cluster. So, typical example is here where you can see a mixed kind of pattern. So, but if you train it well with a more number of data set points, so you will find out that this type of technique will be very helpful for flow regime identification. Next, let us see a new type of methodology where we will be trying to find out the oscillatory flow through an airlift loop. Okay, here in this experiment we will be using conductivity probe signals, pressure transducers and magnetic flow meters. Okay. And for signal processing we will be using PSDF, probability spectral density function, cross correlation, auto correlation, attractor and time delay plot. So, as you have already understood, this is having conductivity probes, we are having multiple sensors over here, and different signal processing we will be elaborating in this. So, this is a schematic of the setup. As all of you know that airlift pump will be having one tank over here, and we will be having one riser. So, this is riser and this is actually downcomer. So, through which liquid comes down, and from here it once again moves up. Now, in the downcomer section, what we have done, we have given the magnetic flow meters over here. Okay. Also, we have given your conductivity probe at 0.6 over here you see, and we have also given some pressure transducers in 0.7. So, you can find out that we are having all three types of measurements over here: conductivity probe, magnetic flow meter and pressure transducers. So, let us see how using this we can find out the regimes. Little bit details about the conductivity probe we have given over here, which we have already discussed earlier. So, this conductivity probe is having a ring type of active probe. Also, we are having a central probe which is kind of ground. So, we will be taking signal between this ring type of probe and this central probe. The cross sectional view we have shown over here. So, this is your pipe section. So, along with this we have the fused ring type of probe, and this is your central probe. Central probe can traverse along the pipeline, that means go towards the center, as well as it can come to the periphery, and we can have the signal between the ring probe and the central probe. So, this is a mechanical arrangement through which we can traverse the central probe towards the axis. Okay. Next, let us see this technique, whatever I have told you, we will be having a central probe. So, this central probe always gives you point based measurement. Why point based measurement? Because it will be sensing the flow of two phase at a single point. So, this is a single point which is actually bare. Apart from that, in this side we will be having electrically insulation. So, we will be finding out that as it is point based measurement, it will be also involved with some sort of deformation of the bubble. Let us say the bubble whenever it is moving up, that may be spherical or some spheroidal kind of thing, and whenever it is coming in contact with the probe, that can deform in this fashion. So, those errors will be coming into picture in this type of cases. Okay. Now, here I have shown you some typical signal. If you find out over here, so you see this high voltage whatever we have obtained, these are for liquid contact, and low voltage whatever we have obtained, those are for gas contacts. So, if you try to find out that how many times we have for this high voltage and how many times we have for the low voltage, so that will be coming as summation of T for the gas and summation of T for the liquid. So, your void fraction will be summation of T gas divided by summation of T gas plus summation of T liquid. So, this is very idealized case we have talked about, but in as it is point based measurement and I have told you there will be deformation. So, actual curve whatever you will be finding out for voltage and time is like this. Okay. But once again, you can do little bit of filtering of this one, and you can once again use this kind of analogy for finding out the void fraction. Next, let us see that how using these signals we can go for PSDF, probability spectral density function, and we can evaluate the pattern of the two phase. So, here you see we have given you the raw signal with respect to time. This is actually the downcomer pressure drop signal from your pressure transducers. So, you see we are having downcomer and riser pressures over here, which are very much erratic to see. Now, if you go for the probability density function, or let us say power spectrum density function of this one, then you will be getting something like this, which signifies high peak somewhere over here, high peak somewhere over here, and you see the nature of the primary peak and secondary peak is always having a falling nature, right. So, if we go for the cross correlation between the signals of the downcomer and riser, then you will be finding out cross correlation gives you something like this. Okay. So, this is at very low air flow rate. So, air flow rate we have chosen here as 9.44 into 10 to the power minus 4 meter cube per second. Okay. Once you increase the flow rate, you see here it is almost double. So, 18.9 into 10 to the power minus 4. So, it is double whatever I have shown you in the previous one. Here you see the signal becomes very erratic, because once you increase the air flow rate, you will be finding out that lots of bubbles are actually interacting amongst themselves and they are forming a bigger bubble. So, here you see the PSDF also looks like very much chaotic, and if you try to correlate, that means the cross correlation, then you will be finding out it is not showing earlier nature whatever you have observed in the previous one. Okay. If you increase the velocity further, you will be getting far erratic nature. Another important technique I will be showing you apart from this PSDF, that is called actually scatter plot. So, what we are having the signals like this, let us say at different times we are having signals like this. Now, what we can do, we can, let us say the signal is in column. So, I will be calling those signals as, let us say Vn, Vn plus 1, Vn plus 2, Vn plus 3 like this. So, n are the different time levels. So, what we can do, we can plot the signals like this in a voltage plane or signal plane like this. This is for the voltage at or the signal at n plus 1th time step, and this is nth time step. To give you little bit more idea, it is like this, that let us say you are getting the signals like V1, V2, V3, V4 like this. So, first we will be plotting V1 comma V2, in the next instance we will be plotting V2 comma V3, and subsequently V3 comma V4. So, abscissa and ordinate will be altering each other. So, you see in this case at low flow rate you are finding out two lobe things like this. Okay. So, once you increase the flow rate, then you will be finding out, here I have shown based on the flow rates, you see once we increase the flow rate, this two lobe thing is forming into three lobe, and subsequently it is actually increasing the scatter once the velocity is increasing. Okay. Continuing like this at very higher velocity, you can find out it is becoming very erratic, showing the erratic nature of the two phase distribution. Okay. Corresponding PSDF also I have, probability density function I have also shown you over here, which is also very chaotic. So, showing a chaotic nature inside the pipeline. So, by doing this kind of post processing of the signals, what you can do, you can find out what type of regime is occurring inside the pipeline. Okay. Next, I will be giving you further idea about the signal processing. So, from 2D plot I will be showing you a 3D plot, which is called a time delay plot. In case of 2D plot, you are having V n plus 1 and V n. Here I will be showing you V n plus 1, V n minus 1. So, in x, y and z coordinate respectively, you can take all these points. If you are having a series of points in a column, so you can always choose 3 consecutive points one by one, and you can plot it in a 3D plane. So, then in 3D plane it will be looking like this. Okay. It is a this 3D plot is actually for z equals to minus 100 millimeter of the channel. Okay. Okay. After that I will be showing you a technique of data fusion, okay, in using our tomographic probe. So, here in case of tomographic probe, we know that we are having optical sensors. So, we are having here optical sensors in the periphery of the pipeline. So, lots of optical sensors we have given in the sector, you see, and all those signals are actually coming out over here in the readout, and then from the readout we are going to the data acquisition system, and finally reconstruction is being done for the interface. Now, I will explain little bit about this type of reconstruction. So, here I have shown you this technology, reconstruction technology, using wire mesh conductivity probe signals. So, here in wire mesh sensor, the pipeline is actually constructed in the form of a wire mesh. So, you see this is a numerical mesh kind of structure. Okay. So, this numerical mesh structure will be getting the voltages. To give you more detail, here I have shown you the schematic. Let us say this is the pipeline through which the Taylor bubble is flowing. So, here what we have done, we have given two sets of wires, okay, parallel wires. First one is here, which we can call as passive section, will be at the bottom layer. There we will be having wires parallelly like this. Okay. At little bit top of that we will be having another layer where the wires will be in the cross direction. Okay. And those two wires, those two array of wires will be coming into picture in case of wire mesh sensor. So, lower one we can call as signal provider, and upper one we can call as receiver. Okay. So, using this signals, what we can do eventually, let us say this is a schematic of this wire mesh sensor. So, here you can see both the layers are actually superposed, and figure has been taken from top. So, you can find out that this vertical wires whatever we are having, those are actually coming from the receiver circuitry, and whatever horizontal wires we are having, those are coming from transmitter circuitry. So, power is given to this one. Okay. Now, what you can do at each cross point, you can find out the voltage. As you are having a mesh kind of structure. So, from the mesh structure you at every point you can find out the voltage. Now, this voltage you can record somewhere, with respect to time that voltage will be moving up, and you can find out that after some time, if you do the reconstruction from those voltages, easily the interface contour whatever has been passed through that mesh structure can be obtained. Okay. A typical example I am showing you over here. I have shown you in the previous slide that it was taken for a Taylor bubble. So, you see this was a Taylor bubble moving in the upward direction. So, after reconstruction we can get a similar type of Taylor bubble shape. So, if you go for more number of wires in the mesh, then you will be finding out a better accurate interface over here. right. So, this is something related to your interface reconstruction. Now, to summarize, in this lecture what we have done, we have understood different sensor techniques over here, okay, and we have understood how signal analysis can be done to obtain the features from the two-phase flow occurring inside the pipeline. So, here we have discussed about neural network based data fusion. In the first example I have shown you. We have also talked about power spectrum density function, PSDF. In the second lecture we have talked about that. Attractor, scatter plot and interface reconstruction also we have stressed. In the third part we have talked about attractor and scatter plot, and in the last portion we have talked about interface reconstruction. Okay. So, overall in this lecture we have understood what are the essence of two-phase flow measurements and how using signal analysis the quantitative and qualitative data can be obtained. Okay. At the end of this lecture, let us test your understanding. So, we are having 3 questions over here. First one, which methodology is not appropriate for two-phase signal analysis? We are having 4 answers: attractor in part A, probability density function in part B, Laplace transformation in part C, and finally part D, power spectrum density function. So, as you have browsed both the lectures, probably you have understood or learned so many times about attractor, probability density function and PSDF, power spectrum density function. So, only the unknown thing is over here as Laplace transform. So, the answer is Laplace transform, right. Let us go to the next question. How many modes in scatter plot can be observed from a signal obtained in slug flow? Okay. So, you are having slug flow. So, how many modes you can obtain from there? Modes means how many clusters you can obtain in the scatter plot. So, definitely as you are having gas contact and liquid contact, you will be finding out that we are having 2 modes. Here we are having answers 1, 2, 3 and multiple. So, obviously the answer is 2 mode, right. Third question, to obtain auto correlation, how many sensors is or are necessary? So, if you have to have auto correlation, so how many sensors are necessary? So, we know that for auto correlation only single sensor data will be sufficient. So, here answers are 1, 2, multiple and then 1 conductivity, 1 optical. So, obviously answer will be single sensor is sufficient. Okay. So, with this knowledge we will be ending this lecture. Thank you very much.